In our previous lecture, we have learned differential equation of small free undamped oscillations. I'll remind this. Differential equation of small free undamped oscillations. Differential equation of small free undamped oscillations. This equation can be written in this way. Second derivative plus omega 0 to the power of 2x, x equal to 0. And this equation has the solution x is equal to xf cosine omega 0 t plus alpha where omega 0 is natural angular frequency, frequency of small free undamped oscillations, has natural angular frequency. I'll just write natural angular frequency. This is natural angular frequency, and nu 0 is equal to omega 0 divided by 2p this is natural linear frequency. Is natural linear frequency. And T0 is a period this is 1 divided by nu 0, or this is equal to double p divided by omega 0, and this is a period of small free undamped oscillations. Small free undamped oscillations. So it was on our previous lecture. This equation was solved, and we began to solve differential equations of small free damped oscillations. I'll remind this. I'll remind this equation. Small free damped oscillations. It is very similar. Is very similar to equation that was before. Very similar, but it has one more term. It has first derivative, and 2 beta dx dt plus so this is differential equation of small free damped oscillations. Small free damped oscillations. And we have made substitution. I just need to frame this in red. I just need to frame this in red. And we have made substitution. X is equal to gamma y, where gamma is equal, where gamma was equal to exponent of minus beta t. Exponent of minus beta t. Minus beta t. And after this substitution, we have obtained that equation will have this view, this form. Plus 1 divided by gamma, second derivative, plus 2 beta divided by gamma first derivative d gamma dt first derivative, and plus omega 0 to the power of 2 y, and is equal to 0, and this is equal to 0. Okay, and to complete our substitution, it is necessary to transform this expression in brackets. Let's do this. So if gamma is equal to e to the power of minus beta t, first derivative will be minus beta e to the power of minus beta t, and the second derivative will be will be equal to beta to the power of 2 e to the power of minus beta t. Okay, and after this we can find the expression in brackets. It will be equal to. So let's use this formula. Let's use this formula, and we will obtain beta to the power of 2 minus 2 beta to the power of 2 and plus omega 0 to the power of 2. And this will be equal to omega 0 to the power of 2 minus beta to the power of 2 minus beta to the power of 2. Okay, do you have any questions about this? No questions. Okay, if there are no questions, let's complete our substitution and transformation, and we'll get here we have brackets and y, and this is equal to 0. This is equal to 0. Okay, do you have any questions about this? No questions. If there are no questions, I will clean some unnecessary things. I'll clean some unnecessary things. And as you can see, we have obtained simplified differential equation, and moreover, I can rewrite this substitution using this gamma. I'll rewrite this in next way: minus beta t multiplied by y. Multiplied by y. And after doing this, we have, so after this substitution, we have obtained simplified differential equation where y to be found, and it can be written in next simple way. It can be written in next simple way. Omega f the power of 2 y, and this is equal to 0. This is equal to 0. Where we have written that omega f is equal to square root of omega 0 to the power of 2 minus beta to the power of 2. Minus beta to the power of 2. Okay, do you have any questions about this? No questions. Okay, so it is necessary to notice. I will just clean some things. And it is necessary notice that here we consider a case when omega 0 natural angular frequency is more than damping coefficient. If this condition is not true, free oscillations will not occur. If this condition is not true. Free oscillations will not occur. Okay, so let's return to this differential equation. As you can see, if we compare this equation and this equation, so these two equations, they are almost the same. They're almost the same. So we can write a solution of this equation. A solution of this equation. So it will be y is equal to xf multiplied by cosine omega f to the power of 2t plus alpha. So this is the solution. Okay, do you have any questions about this? No questions. Okay, if there are no questions, then I will clean one more unnecessary formula. It was necessary, but we have used this. We have already used this. And after substitution, after using this here, we will obtain that it will be xf e to the power of minus beta t cosine. But why have I read this? Cosine omega ft plus alpha. Cosine omega ft plus alpha. Okay, what questions do you have about this? So we have found the solution of differential equation of small free damped oscillations. Small free damped oscillations. We have found its solution. Okay, and beta. Beta is damping coefficient. Damping coefficient. Beta is damping coefficient. Beta is damping coefficient. And I'll remind that sometimes you may see in the internet that damping coefficient is beta divided by omega 0. So sometimes you may see this relation called damping coefficient. But we will use this definition. We will use this definition, and what is necessary to write? It is necessary to write that omega 0 is natural angular frequency. Natural angular frequency. Angular frequency. Natural angular frequency. And this is angular frequency. Angular frequency of small free damped oscillation. Angular frequency of small free damped oscillations. Small free damped oscillations. And this new f is equal to omega f divided by 2p divided by double p is linear frequency. So it will be linear frequency. Linear frequency of small free damped oscillations, and TF is sorry, I will write a formula. 1 divided by nu f, and this will be double p divided by omega f, and this is a period of small free damped oscillations, of small free damped oscillations. of small free damped oscillations. Log of small free damped oscillations. Okay, what questions do you have about this? No questions. No questions. Okay, if there are no questions, you can see the difference. You can see the difference between these equations, and I will just remove. I'll just remove this value y. And sorry, I have some trouble with power. We have this in Kiev. Some troubles with electricity, and now disconnect may occur. Because of trouble with power. Okay, so let's return to our equation. So you can see that the difference between these two solutions is that here we have e to the power of minus beta t. This is a monotonic dissipating function. Monotonic dissipating function, and it decreases. It decreases with time. It decreases with time. So you can see this is the difference. Okay. If there are no questions, let's remove. Let's remove left red frame because formula in left red frame is a partial case of formula in right red frame. So let's remove this, and I will leave just this. Okay, so what else can we say about free damped oscillations? Sometimes we have or you can see in the internet. You can see in the internet value that is called as logarithmic decrement and amplitude. Yeah, let's look at amplitude. Amplitude. What is amplitude? Amplitude is this multiplier near cosine. Multiplier near cosine is amplitude. A as a function of time t is equal is equal to xf. Xf is a constant. Xf e to the power of minus beta t. No, sorry. Here we have just time t. This is amplitude. Amplitude. And to describe dissipation of energy, it may be often used such value as logarithmic decrement. Logarithmic decrement. According to the definition, logarithmic decrement according to the definition, it is equal to natural logarithm of amplitude in moment in time t divided by amplitude in moment of time a in moment in time a plus t plus tf. So this is logarithmic decrement according to the definition. And sometimes you may see another formula. Sometimes you may see another formula, and now you will see that this is the same. 1 divided by n. 1 divided by n. Natural logarithm a at the moment in time t divided by a t plus n t f ntf. So let's make substitution. Let's make substitution to calculate this logarithmic decrement. 1n ln natural logarithm x f e to the power of minus beta t and xf e to the power of minus beta and t plus n t f and tf and tf and and this will be 1 divided by n natural logarithm after division we will get e to the power of n beta t f and beta tf, and it will be 1 divided by n beta tf and beta tf, and it will be just beta t f. So as you can see, logarithmic decrement doesn't depend on this value n. In case when n is not equal to 0. N is not equal to 0. In this case, logarithmic decrement doesn't depend on number n, because it will be beta tf in any case. So we can write that logarithmic decrement is equal to this. Is equal to this. Is equal to this. And I have written both this formula, this and this, because both of them you may see in the internet and in different reference books. You may see both these definitions, but as you can see, they are the same. They lead to the same result. Beta TF. Okay, and one more interesting value that is known as quality factor or Q factor. Quality factor. Quality factor or Q factor. Quality factor or Q factor. What is this? Or maybe without hyphen. Quality factor is quality factor according to the definition. Is equal to p divided by logarithmic decrement. And it will be equal to p divided by beta tf, it will be beta tf and it will be equal, if we remember that f is equal to p divided by omega f. If you remember this, we will obtain omega f divided by 2 beta. So this is the quality factor or Q factor. And the Q factor shows the ability of system to conserve its energy. Ability of oscillation system to conserve its energy. Okay, what questions do you have? What questions do you have about damped oscillations? No questions. No questions. Okay, if there are no questions, so let's continue. Let's continue. Let's try. Let's start learning forced oscillations. Let's start learning forced oscillations, and I will begin again with simple harmonic oscillator. With simple oscillator, I'll remind that this is just spring connected to the fixed wall. So we have spring, and we have mass. We have mass m. We have mass on the spring, mass m. Spring constant is equal to k, and some dissipation coefficient is equal to mu. Coordinate axis is x. Coordinate axis is x, and here we have 0. Here we have 0, and here we have that, for example, velocity of this mass v is equal to first derivative dx dt multiplied by ort I, and we have that we have one force. We have one force. I will write this force as Fs. Fs is equal to minus mu. Sorry, we have Fs. Okay, so from our previous lecture, we know that this force Fs, or projection of this force on axis x, is equal to minus mu dx dt minus kx. It is from our previous lecture, and let's add one more force. Let's add one more force, a periodic force. Let's add periodic force F. Let's add periodic force F. Let's add new force. And this force, according to the definition, is periodic. F is equal to Fm multiplied by cosine omega t, where omega is some predefined angular frequency. Okay, and how to write the dynamic equation? We can use the second Newton's law of motion. According to the second Newton's law of motion, we have that m mass second derivative of coordinate, and it will be equal sum of forces. So it will be Fs. It will be Fs plus F plus F. Fs plus F. Okay, so let's substitute them into the dynamics equation, and after this substitution, we will get next equation. Let mu and plus Fm cosine omega t plus Fm cosine omega t plus Fm cosine omega t. And let's make some transformations. We will get that it is equal to second derivative plus mu divided by m dx and dt plus spring constant divided by mass m x, and this will be Fm divided by m cosine omega t. Cosine omega t. Cosine omega t. Okay, do you have any questions about this? No questions. Okay, if there are no questions, we can see that the dynamic equation of simple harmonic oscillator in case of forced oscillations. So differential equation can be written in this way. Okay, if there are no questions, I will clean this picture. I will remove this picture. And it is necessary to say that this equation is true for any small forced oscillations. And if you compare this equation and this equation, you will see that the difference is that this equation has non-zero right part, and this equation has zero in right side, in its right side. Okay, so let's continue with it. Let's continue. Let's continue. I can rewrite this in a simpler form. d2x by dt2 plus 2 beta dx dt x dt plus omega 0 natural angular frequency to the power of 2 x, and it will be equal to this. It will be equal to this. Okay, and just left for a while this equation, and have a look at the next system. Have a look at the next system from electricity and magnetism. Okay, let's have a look at so-called RLC circuit. What is this RLC circuit? In this circuit we have resistance, resistor, capacitor. We have resistor, capacitor. All elements are connected in series. So here we have capacitor. Here we have capacitor. And here we have source of periodic EMF. So it can be written as this. And here we have inductance. Here we have inductance. So we have R, resistance, inductance, capacitance, and electromotive force. Electromotive force that is equal to Um cosine omega t. So let's try to understand what happened in this system. Let's try to understand what happened in this system. Let's try to understand. We can use that if we have we can use next information about connection in series. As you know, for connection in series, voltages add to each other, and for electromotive forces, the situation is the same. We should add them if we have a connection in series. So I mean that electromotive force here plus electromotive force of self-induction that occurs in inductance, and it will be equal, this sum will be equal to, voltage across resistance plus voltage across capacitor. And now it is just necessary to write these terms. It's necessary to write these terms. According to the definition, or according to the condition, E is equal to electromotive force is periodic function of time, and it is equal to cosine omega t. Okay, what about electromotive force of self-induction? According to Faraday's law, it will be minus L and first derivative di dt, and it will be if we remember that, it will be, if we remember that electric current is equal to first derivative of charge, we will get that it will be minus L d to the power of 2 q and d t to the power of 2 dt to the power of dt 2. Okay, what about UR? What about voltage across this? According to Ohm's law, electric current is equal to UR divided by R, and it will be, so from here we have UR is equal to R multiplied by electric current, and it will be R dq dt, dq and dt. And the last, you can remember from our previous lectures that capacitance is equal to Q divided by voltage or potential difference across capacitor. So from this we will get that UC is equal to electric charge divided by capacitance. Okay, and what can we get from here? Let's remember our equation, and let's make substitutions. And and we will get that um cosine omega t and minus this UR is equal to this. So here we'll have and plus U divided by C. Okay, do you have any questions about this? No questions. So if there are no questions, let's rewrite this equation in more traditional form. So we will get second derivative of electric charge plus LR resistance divided by inductance, and first derivative plus charge Q divided by LC, and this will be equal to UM divided by L and cosine omega t. Cosine omega t. Okay, do you have any questions about this? No questions. Okay, that's great. So I'll remove some things. So we have differential equation for this RLC circuit. Okay, and let's compare. Let's compare differential equation for simple oscillator. Let's compare differential equation for simple oscillator and differential equation for electric oscillations in this circuit. We can see that these equations are very similar. It is so we can just change x and q, change x and q, coefficient mu and resistance R, and mass and inductance, spring constant key, and inverse capacitance, and force, and voltage. And so if we make these changes, we can obtain one equation from another equation. So you can see that these equations are almost the same. So if we solve one of them, we will get the solution of another equation. Okay, so let's remove this equation from mechanics. We will in future we will study electrical oscillations. Okay, and let's try to let's do this change. So x should be changed with x should be replaced with charge q and u and q and um instead of fm, and inductance instead of mass m. Okay, so we have obtained differential equation for RLC circuit, and here it is necessary to write that beta is equal R resistance divided by double inductance, and omega 0 is equal to 1 divided by square root of LC, and this is damping coefficient, coefficient, and this is natural angular frequency. Natural angular frequency. Natural angular frequency. And this is natural angular frequency. So for RLC circuit, we have such differential equations. Such differential equation. So this is a differential equation of small forced oscillations, in RLC circuit. In RLC circuit. In RLC circuit. And on our next lesson, we will try to think how to solve this equation, but it will be on our next lesson. Okay, what questions do you have? No questions. If there are no questions, so thank you for your attention, and I hope to meet you next week.